Hello, good day. So this is now the 15th video on our linear algebra series. So last time we ended chapter 6, which is on inner product spaces. And then we have the following topics: orthogonal complement and then the minimization problem. And then notice here that I have mm, I have difficulty in getting to use with my new setup, like screen protector, something like with my handwriting. Anyway, so here today we will start chapter 7 of Axler's book. Chapter 7, we have the following keywords. We have the adjoint, the normal, then self-adjoint, spectral theorem, isometries. So that's it. So again, we have F. We will just work on either our set of complex numbers or field of complex numbers or just a field of real numbers. And then our V here and W will denote inner product spaces, which are finite dimensional. So convention, let me write them down. So your convention is the following. If you have F, such R or C, and then V here is finite dimensional inner product space over our field F here. And of course, it can be your letter W. So this is our convention. And then here, these are vector spaces. Of course, inner product spaces are vector spaces. And now let's start with the first topic for today. So the topic for today is self-adjoint operators and normal operators. Let's start. Let's begin by defining normal as self-adjoint operator. But first, if we need to define what's an adjoint. So here, T is a linear map from V to W. And then the adjoint of T, our T here, is denoted T star. This is a map from W to V such that the following is true. So if you get the inner product of TVW, it's just equal to V inner product with T of W here. This is for every V in the vector space B and every W in the vector space W. Now, before going further, I would like to mention that the word adjoint here, as remarked in the book, may be used in some sense in some other linear algebra books or lectures, but here, if we will not be dealing with them. So, but in case you encountered this term adjoint, just verify that this coincides with the adjoint, that the notion of adjoint that we have now. Okay. Now, let me have a remark on this definition of our adjoint. So suppose that this makes sense. The above definition makes sense since if you look at T in the linear map from B to W set, LVW, and then if we get and then we fix here, say W in the big W, and then consider the linear functional. Say the linear functional is given by this. So linear functional, it's just a map from V to F. And then this linear functional here is a map from V to F. And then this is given by, if you get a V here in V, you map it to the inner product space of inner product of T of V and W. So here, if we have a linear functional here, notice that this linear functional here, this depends on our T and our fixed W and W. Okay, so using Rice representation theorem, so this is by representation theorem. If we have a linear functional, there exists a unique vector in V. There exists a unique vector, say M in V, such that this linear functional is given by the inner product. That is, this right to V is just equal to V and M. Wait, V and here and M. Okay, this one is for, yeah, and then the claim here is this is for every V in the inner product space V. And then, in fact, we call this unique M the adjoint, the unique vector M. We call M the T star of W. So, in other words, this is the unique vector such that T of V W is equal to, in other words, W and then T star. No, that's not W. That's supposed to be, it's just V T star W. Okay, so this is a quite theoretical, as I have mentioned before. But let us recall some familiar example that you have from your early linear algebra class, or from your, maybe if it's new to you, then we can study it together. So, for example, if we get a map from R3 to R2, okay? And then this map is given by x1, x2, x3, is mapped to the ordered pair x2 plus 3x3, and then 2x1, the second component. So here we get to find the formula. Now, find a formula for our T star, or the adjoint of T. So here, solution, T star is a linear map. It's a function from R2 to R3. So here, we have to fix our ordered pair y1, y2 in R2. Then, for every ordered triple in R3, of course, your inner product of x1, x2, x3, and then T star of y1, y2 is equal to the T of x1, x2, x3, and then y1, y2. So we need to find our formula for T star, or the adjoint of T. Let me write here. So this is by a definition here. This is just, the first component will be x2 plus 3x3, and then 2x1. And then the second one is y1 y. This is an inner product. Now, if you have you operate this as dot product, so we get here x2 y1 plus 3x3 y1, and then this one here multiplied by this, and then this one here multiplied by this, then what? This is for the first part. And then for the second part, we get 2x1 y2. Okay. Now, if you look at this, this can be expressed as x2, x1, x2, x3. No, it's parentheses. And then we get here, what's the partner of x1? 2y2, and that's the partner of our it's the partner of our x2. X2 here is first x2, y1, and then the partner of x3 is 3y1. Okay. So that means your P star of y1, y2 is just this 2y2, y1, and 3y1. Okay, that's it for our first example. For the second example, we get fix u in the vector space V, and fix and x is arbitrary element of W. T be a linear map from V to W, defined by T of V is just the inner product of V and U, and then multiplied by X. This is for every V and V. So find a formula for our P star. Solution. So you have to, here you have fix your W in here in the vector space W. Then for all V in the vector space P, we get V P star of W. It's just T of V W. So we know T of V, this is just V U X and then W. And what? What's next? Via property of inner product, we can put this one V U outside, and then we have X W. Then after that, you can what? You can put the XW inside, yeah, V, and then we get by conjugating this, you get W X times U. So this one is conjugate from the definition. And then it's not the definition, but property of inner product. Here you put this one inside. Here it became bar of XW, but bar XW is inner product ng WX. That's it. And therefore, your T star of W is given by the inner product of X and W and X multiplied by your vector. Notice that this is a real, a field element, scalar. In the above definition, the T star is not only a function, but it is in fact a linear map. So here, T star is not just a function. And then in fact, we can state this as a theorem that if we get T a linear map from B to W, then you get T star also a linear map from W to B. Of course, how do you show this is a linear map? Check it. It follows the closure under plus and scalar multiplication. So now we are going to provide here some properties of a joint. First property, if you have S plus T adjoint, this is just S adjoint plus T adjoint. This is for all S and T in LVW. And then number two, lambda T adjoint is just lambda conjugate T star. This is for all lambda in F and for all T in lambda VW. I'm repeating that over and over again. And this third one, I will not. So this is T star. Star, the adjoint to the adjoint gives you the original T. Number 4, you get I. Adjoint is just I. I is the identity on B. It's the identity operator. And then number 5, you get ST star. It will reverse order. So ST star is just S star, T star, S star, or T adjoint, S adjoint. So here, for all T in L, V, W, and then for all S in L, W, U, here U is an inner product space over F2. V and W and U are all inner product space. We will provide proof to some of them, but not all. Of course, for the A, you just need to check the closure. Just check EC, A, B, just check, for example, just check your A, your A. For example, we will do B. Suppose that lambda is an F, a field element, and we get T a linear operator or linear map. If we have V in our V and W in W, then by definition, V T star of W is equal to lambda T V and then W. And then this is just lambda, and then you get T V W. So, but here we can put this lambda, and then here we get V, and then this is T star W by definition. And here we get V, and then if we put lambda inside, it becomes a conjugate, and then T star W, which gives us your lambda T star is just lambda conjugate T star, as we have required for the second claim. Okay, so for letter number 3, I think what's number 3? Yeah, T star star will give you the original one. So let me do number. Okay, the numbering. So it's supposed to be. Okay, let me change the letters. A, B, C, D, E. And then for example, I will do again number letter C. So for letter C, so T here is an element from the linear map BW, and then V an element of V, W element of W. Then by definition, W T star of T star star of V is just T star of W V. Okay. This is also just if you the interchange sign, you get the conjugate V here, then T star of W. Okay, if you operate inside, you get the conjugate and then TV, and then you get W. Okay, and then by a conjugate, you get W and TV. Thus, your T star is just your T. Okay, so they are easy to follow, and the others like D, E are left for reading. So let us now consider the following claim, and then of course I will not prove again most of them. So theorem which relates the null space and the range of T star or the adjoint in terms of the null space and range of our original operator or linear map T. So suppose here T is an element of LVW. Then we have the following claim. First claim is the following. The null of T star is just equal to the range, the annihilator of the range of T or no, it's not the what do you call this? This is the orthogonal complement. This is the orthogonal complement. So recall the definition of orthogonal complement. This is just the set of vectors V such that V times U, the inner product of V and U, is 0 for every U in the range, or I mean in the set or the subspace. So that's okay. It's a 6.45 definition of the book. I think it's nice to get some hold of the book while the class, and then you can pause sometimes the video and then verify or maybe spot the errors in my statements. We can do that, of course. And then I would like to remind this a video is not edited, so maybe there's some error, but very minor, of course. But some maybe major, but I don't think so. The second claim, letter B is A, C here, and D, the range of D adjoint is equal to the null of our T orthogonal complement, then the null of T, and then the range of D is just equal also to the range of T star orthogonal complement perp and this is just the null of T star perp. Then we will prove one and then leave the others. So for A, how do we prove letter A? So that W be in W, then we get W is in the null of our T star. This is if and only if T star W is equal to 0. This happens when T star W and V is their product is 0 for all the vector V and V. And this is also true when we get TV here and then W is 0. This is for all V and V, and which is also true when W is in the range of T perp. And then this means that the null of T star is just the range of T perp. So as desired for letter A. So if we take orthogonal complement of both sides, I'll say, say, so here we get, say, null T star equal to range T perp. And if you get the perp this, then you get perp this will give you now T perp equal to the range of T. This is proves our letter D. Okay, so the rest are the same flow of proof. Now, let us define conjugate transpose. So, transpose of M by N matrix over over F. So this conjugate transpose is the N by M matrix obtained by interchanging rows and columns, and then taking complex conjugate of each entry. Example, if we get 2, 3 plus 4i, 7, and then 6, 5, 8i is our, what's the operation? And then this is M. The conjugate of M is just, we get 2, 3 minus 4i, and then 7, then 6, 5 minus 8i. So they have interchanging columns and rows. So you have a remark if F is just R, the conjugate transpose is just transpose because we don't have the complex conjugate. I mean, the complex conjugate of real number is just itself, the real number. Now, the next theorem, the adjoint of linear map does not depend on the choice of basis, and this explains why this book emphasizes adjoints of linear map instead of conjugate transposes of matrices. Okay, let me do that as remark. Adjoint of our linear map is independent of the choice of basis. That's why we deal with adjoint of linear maps instead of conjugate transpose of matrices. So here, the next result, we get the relationship of the matrix of the adjoint with the matrix of T, but warning, the next result need orthonormal basis to deal with normal basis and not true in arbitrary non-orthonormal basis. So here there's a warning, which is that's why we are. This is to emphasize this non-independence of choice of basis for an adjoint of linear map. But when we speak of a matrix, it has to be the choice of basis should be orthonormal. Okay, let us quickly write or explain the theorem. The proof here, I will be leaving the proof for you. So the idea is if you get the linear map, and then we get a matrix, and then suppose that E1 to En and F1 to Fm, this is orthonormal basis ng V. This is orthonormal basis of our W. Then your matrix of the adjoint with respect to F1, Fm, then E1 base for N. This is base for basis for of our W. This is of V. This is equal to the conjugate transpose of our matrix M T, then E1 En, F1 Fm. So this is like if you get a map or a linear map, and then we have the matrix of that linear map, then the matrix of the adjoint is just the conjugate transpose of the matrix. Okay, I will not prove this. The proof is left as an exercise. Now we go to self-adjoint. The proof is left. We already have defined adjoint. Now we are ready to define self-adjoint. So what's a self-adjoint operator? So an operator P in LV is self-adjoint if T is equal to T star. In other words, TVW is equal to BEW for all V and W in V. Okay. So for example, we get T and operator on F2, and then matrix of T is given by 2B37, and then T is adjoint, self-adjoint, if and only if B is equal to 3. Because since your M of T is just M of T transpose, if and only if B is 3, where this is the conjugate transpose of the matrix E. Okay. And then some remarks. If you have T and T1 and T2 are self-adjoint, and then we have a lambda A scalar, then T1 plus T2 are also self-adjoint, and then lambda T1 is self-adjoint. I will leave the proof of this again. So if you get a complex number Z is real, recall Z a complex number, Z is real if and only if Z is Z bar. Okay. So here the next result is interesting if the field is C, because if the field is R, automatically we get every eigenvalue real. So here, let us consider this too. Every eigenvalue of adjoint operator is real. This is over complex vector spaces. So the proof here is basically using this claim here. So T is self-adjoint, and then element of this, and then let lambda the eigenvalue of our T, then let V not 0 vector in V, such that your T of V is just lambda of V, lambda times V. Then your lambda, the norm of V squared, is just lambda V, V. And this is just T of V times V because of this. And this is just what? T of V is, here we get by being self-adjoint, we get yes, and then what? After that, we get V, and then lambda V. And then after that, we get, since this is here, we get the conjugate of that, and then v, which is just the conjugate times the norm of v squared. Thus, your lambda is equal to lambda bar, which means power is real as desired. So the next theorem is false for real inner product space. Inner product spaces. For example, okay, let me put this here. Example, T in R2 is just rotation by 90 degrees counterclockwise. You get P of xy is equal to negative yx. And of course, here, P of v, if this is our v, is just orthogonal. P of v is orthogonal to v. So this one, because the angle between xy and negative yx is 90 degrees. Although p is not 0. So the next theorem is only true for complex numbers. Over the complex numbers, EV is orthogonal to V for all V only when T is 0 operator. So let us prove this. Let us prove this. In other words, T V equal to 0 for all V and V, then T is just the 0 operator. Here, this is the 0 operator. So it is the operator that maps everything to 0. Okay. I will provide the proof here. This is like trick proof. So we can express our the inner product of TU W as follows. So get for the real part, we get T of U plus W and then U plus W. Yan, and then negative of T of U minus W and then U minus W. This is over 4. So you can check this. Plus, for the complex part, you get T of U plus IW, then U plus IW, and minus T of U plus I, not plus, but minus IW, U minus IW. This is all over 4. You can check that this and this, if you distribute this, it will be, what you will get is TU over 2, and here you get TU over 2 also, and you get this after computation. So verify the right hand side by computation. So this term here, this term here, this term here, this term here, this term here. The blue encircled terms are of form T of V and T of V for some choice of V. Or appropriate choice of V. Thus, in this case, what is TVV? We know that this is 0. So here, everything else is 0. See, T of, this gives us T of, this is 0, this is 0, this is also 0, this is also 0 by this claim here. Thus, your TUW is just 0 for all U and W in V. This implies, since this is true for any choice of W and V, this implies that T is equal to 0. For example, take WB TU. If this is TU and TU, this will give you 0. So we need it to be true for all. So it is only true when T is just the ordinary 0 operator. This claim is proven. Okay, there is another theorem. This is only true for C, and it is not true for R, because uh, if you are considering any operator on real inner product space that is not self-adjoint, this is false. So over C, TVV, the inner product is real for all V only for adjoint. Let me rephrase this. Suppose T is a linear operator or an operator, and then V complex inner product space. Then T is self-adjoint if and only if T of V is an element of real number for all V in the inner product space V. Okay, let us provide proof of this. So let V be an element of V. Then TVV is minus TVV conjugate is equal to TVV minus VTV. Okay, so this one is equal to TVV minus T star of V and V. This means that by a property of a linear operator, this is just T minus T star, okay, V, V. So if T of TVV is in R for all V in V, then this part here is 0. So the T minus T star V 0 for every V in V. That means T star is just 0. Hence, T here is equal to T star. Okay. So suppose suppose that we have on this one is true, it's real, then we get self-adjoint. Now suppose we get a self-adjoint. Self-adjoint, then the right hand side, this one, the right hand side of the equation equals 0. So if that is 0, what happens? Your TV V is equal to T V V. Wait, I'm missing the time. T V for every V in the vector space V. Thus, what can you say if this is equal to its conjugate? Thus, your TV V is an element of R for every V in V as desired. So only for inner product space V, non-zero operator T might satisfy TVB 0 for all V. However, if we have a sub-adjoint and then TV inner product of TV and V is 0 for all V, then we get 0 regardless of it being real or complex. Here, on inner product space V, a non-zero operator T might satisfy. However, the next result will show that this cannot happen for a self-adjoint operator. So let us state that as a theorem. Suppose that T is self-adjoint on V such that your TB is 0 for all Vn. Then T is 0. So earlier, what's the difference? Earlier, we get a complex inner product space, and then we only suppose that P of VB is 0, but here the additional assumption is this is equal to the adjoint. This is self-adjoint, and get TV and V, the inner product, is 0. Will give you a 0 operator. Okay. The proof here is I will explain. Okay, anyway, we just have a few more pages to cover. So let's provide the proof of this claim. So we already proved this without the hypothesis that T is self-adjoint when V is a complex inner product space. So this is okay when V is complex inner product space without T, V, without self-adjointness of our T. So we will prove for real inner product space. So for the real inner product space, that TUW, we can express this as before, as follows. We get TU plus W, U plus W. Again, this is a trick. TU minus W, and then U minus W, all over 4. If you compute the right-hand side, this is our right-hand side, the left-hand side. If you compute the left-hand side, the right-hand side, and then just compute this using this right-hand side, compute using the following. EWU, this inner product, is equal to WT of U, because it's self-adjoint. This is also T of U W, where this one is, the first equality is via self-adjoint, and then the second equality when in real pad space. Okay, that's true for these reasons. So of course, PVV are the form of each term. As before, we get TUW being 0 for all U and W in the vector space B. That means T is 0 as needed. Now we are done with our self-adjoint operators. We'll go to the next one, which is on normal operators, and then we will use these properties of being self-adjoint, being normal operator when we cover our spectral theorem in the next video. Okay, let's define what a normal operator is. First one is the definition of a normal operator. So T here, a linear operator, is normal if and only if your T inverse, T adjoint, this is T adjoint T. That is, it commutes with it adjoint. It's adjoint. Obviously, every self-adjoint operator is normal, and then so obvious if P is equal to P star, then self-adjoint operators are normal. T is just T star T is T star T star T star is just T stars, whatever. Okay. All right, let us consider the following. Example, if you have a linear map P, and then the matrix of P is 2, 3, 3, 2. Then, of course, matrix of T is just this operator is not self-adjoint because the entry in the second row is column 1 is equal to 3, does not equal to the complex conjugate in row 1 of column 2, which is equal to -3. So this is not self-adjoint. The claim is T is normal. So if this is your matrix of T, of course, by some operation, the matrix of 3 adjoint is -3, 3, 2, 2. And here, matrix of T adjoint is just 2, -3, 3, 2, and then 2, 3, -3, 2. This gives us 13, 0, 0, 13. And also the matrix of T star T is just 2, 3, -3, 2, 2, -3, 3, 2. Then you give me 13, 0, 0, 13. Here, pause the video and compute. Of course, you can use hand or you can use our solver. Thus, where T here is normal, but not self-adjoint. Okay. We will now characterize a normal operator. Okay. T in an operator is normal. Okay, I have an extra L. If and only if your norm of TV is equal to the norm of T adjoint B for all V in the inner product space. Let us quickly prove this. So the proof is computational. So T normal, if T is normal, then you can say that T minus T star 0, this because it commutes. If you get this and then operate this with T and T gets 0, for all V in our vector space. This is also true when you get EV, V, V is also equal to T star V, V. Of course, true for all V and this means this one here. Why are they true? They are true because if you look at the why are they true? This also implies that EV is equal to the inner product of T star V and T star V for all V. This means that this is just T of V squared is equal to T star V squared. Of course, this is only true when T of V is equal to T star of V for all V in the vector space V. So this statement here is true statement here. This one is true by a self-adjoint. All right, let us finish today's topic with the following result. For normal, okay, let me suppose T here is a linear operator, is normal, and V is an element here, is an eigenvector of T with eigenvalue lambda, then V is also an eigenvector of the star or the adjoint with eigenvalue lambda conjugate. Okay. The proof here is just computational. So T is normal. So E normal. So implies T minus lambda I normal. So here 0 is equal to the norm of T minus lambda I times B. This is equal to the norm of T minus lambda I star B. This is also equal to the norm of T star minus lambda I lambda conjugate times V norm. This means your V is an eigenvector of our T star with eigenvalue lambda conjugate as designed. And because self-adjoint operators are normal, the following are the next result applies in particular to self-adjoint operators. This is the last one. T here, normal. Then the eigenvectors of T corresponding to distinct eigenvalues are orthogonal. Okay, let us quickly prove this and then end the video. Suppose that alpha and beta are distinct eigenvalues of T corresponding to vectors U and V to eigenvectors. Okay. Thus, by definition, T of U is equal to alpha U and T of V is equal to beta V. And then from our previous result, T star of V is equal to beta V. Thus, from above, thus we get alpha minus beta of U V. This is just equal to alpha U V minus U beta V. So this is just E of U V minus U T star of V. And we know this one and this one. What are these? These are Since we have a normal, and of course, um, and by the normality of t, we get this one is 0 because your alpha is not equal to beta. The equation above gives our u v equal to 0. Thus, u and v are orthogonal since their inner product is 0. Yeah, I think that's it for today. For the next video, we will consider spectral theorem. The first is the complex version, and the next one is the real version. Of course, we can go on with real first, but I think complex number is nice because of this algebraic closure. So we will go with complex spectral theorem first. So I think I'll end here.